All right, hey everybody, this is worksheet 4 on electric circuits. We should be pretty comfortable with this. We've gone over the homework, but I think that this will just kind of serve as a step-by-step and good reference building for that midterm review. Um, just some things to note. I'll be making an announcement for when we're going to be hosting the midterm review. Right now, it's looking like it's going to be Friday evening, and that's just because there's a bunch of there's another SI session Saturday night, and I want to have make sure everyone can do each one, and then Sunday's Super Bowl, and I know that could be like limiting for some people. So we're gonna do Friday. It's gonna be recorded. It's gonna be worksheet and then Q&A, and then especially Q&A based on those midterm review questions. So make sure you send those to me, the one like what you have questions on, and I'll make sure to prepare accordingly. Other than that, I think we can just dive right into this. So let's just first establish some, capacitor resistor comparisons here. So our equation for resistors and for capacitors, Q over C. And then it's just like when they're in series and parallel, the effects of that on their currents and voltages in respect to being the resistor and capacitors. So, resistors in series, we just add them all. In parallel, we do that inverse addition. And then the opposite is the case here, where capacitors in series is that inverse addition, and parallel is just we add them all together. Something to just keep in mind is that the current is the same in series, and the voltage is the same in parallel, and this extends to both of these guys. See parallel, voltage, same, and same thing here, series, in respect to charges, same and same. And so it's kind of, the equations are different, but the current is the same in series, and voltage is the same in series. Just keep that in mind. It's like a helpful table. Other than that, here's our junction rule. Just whatever goes in equals what comes out. Assigning our signs, we do that with like Kirchhoff's rule, loop rule, depending on like which way our voltage drop is or which way our current is. So it's kind of old relative to that. Remember, by definition, the sum of a loop equals 0. So like even if you guess clockwise when you should have gone counterclockwise, so everything comes out as negative, that's okay as long as you're just consistent with that. Other than that, I think we're just good to start off on the sheet. I kind of discussed this already. Just some notable things. Yeah, I mean, I talked about every single one of these. So there's no point to kind of linger on that. So I'm gonna start by saying that questions 1 here and even 2, I'm like very, very sure that they probably would be on the midterm. So yeah, these are some good ones to practice. And I definitely made them. These are like midterm level questions. They're pretty lengthy and like the difficulty and such. So, with problem 1, we're asked to determine the equivalent resistance of the circuit, the voltage across the 6 ohm resistor, and the current through the 6 ohm resistor. So just bear with me as I shrink this blue box over and over again. Initially, we have this circuit right here. Here's kind of that 6 ohm resistor that we're going to be referencing a lot. And we know, like, we just want to start simplifying this to get that equivalent resistance. So if you're doing it very quickly, you can do them at the same time. But I feel like, this is what I told someone the other day at the session. What takes longer than doing each step, doing the whole problem over again. So if you're more comfortable doing each step, just do that. Make sure you get it right rather than doing like 2 things that are in parallel at once. When I say that, I mean like, yeah, clearly these guys are in parallel right here, and so are these ones. So you could do them at the same time, but if you're more comfortable, just do them one at a time. Like, it'll be annoying to redraw, but just play it safe. Or if you're you are comfortable with it, go ahead and do that. Okay, so here we go. We have this circuit. Just right off the bat, like your intuition to kind of lead you to start by doing a parallel right here. So we need to, just simplify that. How do we do that? We do that inverse addition. And now we have this circuit right here. What we're going to do next, again, we're going to see that these guys are in parallel. So we're going to simplify through that same reverse addition. And now we have 2 systems of resistors in series. So there's this guy in series and this guy in series. We're going to still do one at a time. Simplify, that's just through addition here. and we'll get this. We do that bottom one, again, still in series, just add. Now these ones are in parallel, and then in series, and that's it. Now you have your equivalent resistance. Okay. And then of note, it's like you kind of want to know where that 6 ohm is. So we know it's here, and then it still is here. It's now embedded in this 3.75, which becomes embedded in this 15.75, and that becomes embedded in this 1.93. So just kind of make sure you keep tabs on where that value is incorporated. Okay, so what I said, part 1 right here, we're done. Now part 2, we're gonna find the current through the whole system. The current through, I call this diagram E. So we just do V equals IR. I'm gonna cover up so I can explain more stepwise. V equals IR, we rearrange now that we have an equivalent capacitance, and we can find that current right there. Okay. So we both, we know that 1.93 and 2 have the same current because they're in series. Therefore, we can solve for the voltage drop on either one. We're going to solve for the voltage drop in respect to that 1.93 because we know that that 6 ohm resistor is embedded in that 1.93. So, excuse me, I misspoke. You have to use the resistance 1.93 to get that voltage drop. That's right here. Okay, with that, we know that 1.93 is made up of a system in parallel. So that means the voltage is constant here. So that means the voltage drop across this 15.75 is 5.89. We just solve for that. We can now solve for the current that's acting right here. Okay. So next thing we have to use that V equals IR again, except we know we're going to be working with only this one. Oh, and here I just said a little note. Like I said, don't worry about this one. And that's because we know that that resistor 6 ohms has nothing to do with that 2.2. It has to do with this one. So that's why we're going to focus on that 3.75. Again, V equals IR, plug in that current we just found, that 3.75, and we now have a voltage drop that acts right here. Okay. So now we just have to find the current through resistor 6. And here we can just easily do that just because now we have that voltage. Just rearrange V equals IR divided by 6 ohms, we're good to go. You'll notice that there's a little bit of trickery in this question in the direction in which it's asked, that being, obviously you're always going to start with that equivalent resistance. And then it says voltage across the 6 ohm and then current through the 6 ohm. You should know that you'd be solving for voltage first. And that's just because like when you're working backwards, that's the only thing feasible because you need that current to be able to solve for, oh wait, actually, one second. Excuse me, I misspoke. You already solved for the voltage drop across 6. It's 1.4, you already solved that right here, right? So I guess you could have gone either way. That's a null point. Thought of a different kind of question. Okay, so I'm gonna delete this. I'm gonna zoom out, let you guys just take a look for a sec. Is any questions on this one? I feel like this one it's lengthy, it's kind of, annoying, but I mean, because you have to keep very careful with every single step and making sure you're doing the right things and knowing your principles of like when current is constant, when voltage is constant. But it's midterm level, I would say. Okay, so I'm guessing no questions. I'm just going to move on. So this is number 2. Again, this is one I'm pretty sure would be on exam. This is the Kirchhoff's rule. So we're given this diagram. I just kind of cleaned it up and drew it over here. I'm just going to zoom in and kind of explain what I did here. So I even wrote the steps right here. Step number 1, we're going to draw the voltage drops at each battery. And that goes from the plus to the minus terminal, or you can I just do long to short. The long side's always going to be that plus. So we know this one's acting this way. This one's acting this way. Okay. And then you can set any direction for the current. I just wanted to have I1 go here. So I1 and I2 going in, I3 going out. We're next going to draw the voltage drops at each resistor. Okay. And those are, same direction as the current. So the current we know is going this way. So right here, that I3 is going up and to the right. So that voltage drops in to follow. I2 is going leftward. These guys follow that. And this one over here is going to be going leftward. So this one follows that. Oh, and same with this one. Okay. So the next thing, you make your loop. It doesn't matter which one you choose, as long as you're consistent, and then make a junction equation. And people, you probably will always have a system that is just one junction equation, but like how many equations would you have? It's just n minus 1, where n is the number of junctions. So here we have 1, 2 junctions, and so 2 minus 1 equals 1. So one junction equation. Any more than that, I would be surprised, but yeah, just like keep that in mind. Okay, so I just did loop 1 up here, but it doesn't matter which one. It doesn't matter where I start. Could have been, this one could have been loop 1. This whole thing could have been loop 1, as long as I make sure to assign every single sign based on that. Okay, so starting with this R5, same direction. So it's going to be I3 R5 minus V2, and then I2 R3, and then I2 R5. Oh, R2, excuse me. Oh, I see. All right, I messed up. So I2, and this one right here is R4. This one's R5. Okay. Next, so I'm going to do a second loop right here. We're starting with I1. So I1 R2 plus I1 R1 plus V1 minus I2 R4. And then this is where I forgot another minus. I forgot an I2 R3 to write it here, but I solved with it included. So just keep that in mind if you're working on this at home, that there should be a minus I2 R3 here. And then plus V2 equals 0, all equals 0. Here's a junction equation relative to point A. I1 goes in, I2 equals what comes out, 3. So next, we're just gonna, yikes. We're just gonna plug everything in. So I plug in all my resistance values right here. I'm gonna simplify equation 2. I'm gonna plug equation 3, that being this junction equation, into equation 1. And I'm gonna solve for I1, call that equation 4. I'm going to plug equation 4 into the simplified equation 2. And now I have a value for I2. Next, I plug I2 into equation 4. Here we go. And I come out with a negative. Negative tells you your guess was wrong. Like, the reality is the current's going the other way. I would say just make a small note of that and make sure you write it as positive. And same thing here, except that, oops, get the negative there. You're just going to plug I1 and I2 into equation 3, and you're going to write your value as a positive. Notice I plug in the negative right there. Okay, so we're not actually done, because we're going to look for the potential between points A and point D. So how do you do that? Right here. So we're going to find the change in voltage from A to D. So you're just going to add the voltage drops and account for direction. So you just have to define plus and negative. So right to left is positive and left to right is negative. Choose whatever you want. The reality is this equation gets, you're going to absolute value the equation, so it doesn't really matter. We can see that delta V here is absolute value I2 R4 plus I2 R3 minus V2. Plug everything in and you get that delta V. And remember, so I said from right to left would be positive. So that's where, I2 R4 is positive, I2 R3 is positive, and then minus V2. Okay. Let me zoom out. You guys can take a look at that. All right. So this is the last question on this one. Obviously, in person, this takes a lot longer, except to draw each system out. But if you guys have any questions or want to see me do anything stepwise, just email me. So here we have a 12-volt battery, 2 resistors, 2 capacitors, shown below. Let me show you that. After the circuit has been connected for a long time, what is the charge in each capacitor? So that verbiage of long time is very important, as it informs steady state. At steady state, we know there's no current acting over here on these guys. Additionally, remember what I said, in parallel, voltages are the same, and that extends with resistors, and with capacitors. So that informs that the voltage across these guys is all the same. So that's kind of like what I wrote up here. The voltage at this 3.3 kilo ohm resistor is equal to the voltage of the capacitors. So what we're gonna have to do is find the current at this position to be able to find the voltage. I already said that. So we're just gonna first find that equivalent resistance. Then we're gonna solve for the current. And with that current value, we can now solve for voltage. And we know that the voltage is going to be constant between these two. We're already given their capacitance values. So now we just have to multiply by 12 microfarads and 48 microfarads. And we'll come out with our answer for the charges on both capacitors. Okay. So any questions on this one, number 3 or number 2? Just hold for a few seconds. All right, so I guess we always finish faster than I time it out by myself, but that's okay. If you have any, like I said, any questions or you need to see anything hand-drawn stepwise, please let me know. At this point, I've already uploaded the key. Like I said, stay tuned for a midterm review announcement. It's looking like Friday evening, but I will confirm and I'll make sure it's recorded. And I feel like the highlight of that is always kind of a Q&A, especially going over those midterm review questions. So make sure you send me those if you want me to go over them. Like it's hard for me to get those back. Those are long questions and normally require like a detailed explanation and drawing. So those are normally hard for me to do a quick email like Sunday night over. So if you guys want to ask about those, please do those early. Oh yeah, sign in. I always forget to say that. But yeah, thanks guys. So stay tuned. Good luck with the studying and let me know if you have any questions. Stop the recording and ask everybody questions.